So thank you very much for inviting me. It's a true honor for me to talk at the Sharif. I've never had the pleasure to visit Iran, but I have dear friends from Iran from the times I was doing my PhD in California, and I'm keeping in touch with them, and they've always talked so nicely about this university that it's the top university in Iran, as I have been told about that. So for me, it's a pleasure to be here today and share my research with you. So I wanted to introduce myself a little bit. So I'm currently at the Universidad Carlos III in Madrid. This is in the capital of Spain. I'm in the Department of Business Administration. My background is more related to mathematics and also operation research. So I did a bachelor in mathematics, and then I did two masters, one in economics at University of Pompeu Fabra in Barcelona. And the second master was with MIT Zaragoza. It's a specific 9-month master in engineering, and it's very much related to logistics and supply chain management. I did all this education in Spain, in my country of origin. But then I moved to the US to do my PhD. I did my PhD in operation research at the University of California, Berkeley. I did it in the Department of Industrial Engineering and Operation Research. So my advisor was Max Chen. I don't know if you're familiar with him and his research. So naturally, you'll see that there's some research that overlaps with his research, especially the supply chain design part of the talk. So I spent 8 years after my graduation. I graduated in 2012. And after graduation, I went to Purdue University, which is in the state of Indiana. I spent 8 years there. That was also in the management department. So my decision was to move from industrial engineering department and operation research to doing research that was a little bit more applied than the operation research. So applying optimization problems and so on to for business and organizations. So that's I did 8 years. I moved from the States this summer to my new institution, that is Universidad Carlos III. Okay, so that's my background, where I'm coming from, my studies and so on. I wanted to, before I start my talk about the specific paper that I will present today, I wanted for you to have an idea of what I do in my research, what's my research about. And basically this is about, I focus on 4 major topics. So the first one is supply chain design and optimization. Then second one is non-profit operations management. Third is aspects related to sustainability and social responsible operations. Also, I will talk a little bit. And then the fourth aspect is more applied. So I like to do applied research, like working for companies and organizations to help them improve their operations, right? So that's kind of, these are more applied research. They can be publishable or not, but they are certainly very refreshing, and they keep me, in touch with organizations and see what their problems and challenges are, and I try to help them. So within the first block of my research, I had done research on conic programming, so how to use conic programming to solve supply chain design problems. I invite you to check out my papers. This was an OR journal paper that showed to be influential because it was a new way of solving supply chain design problems. Today's paper will be related to supply chain design. It will be about aid distribution of, in the case of the paper, food distribution, but it could be any sort of supply that needs to be distributed as in the form of aid. The second block that I started after my first block was the nonprofit operations one. Of course, all the blocks have they overlap with each other. So I'm doing my research right now more focusing on the second block. The second block is looking at organizations that are not for profit and how they can improve their operations. A lot of research has been done for profit organizations, looking at their inventory models, looking at production models, any sort of operation decision, right? Also supply chain design. So what I'm doing with this research is to try to revisit some of the operational decision problems and looking at how a nonprofit organization should solve them. And there are differences because nonprofit organizations, they don't have a maximization of profit objective. So the first question is, what is the objective that the NGO, a nonprofit organization, should use or is using? And then there's also the aspect about the donations. So nonprofit organizations receive donations. Donations could be in the form of in-kind. It could be in the form of monetary donations. They could be also in the form of time, like volunteers that volunteer their time to help the organization. So the incorporation of these donations into the organization of the company and the operational decisions of the company. This, I think, is a very challenging aspect to study, and that's what I'm devoting most of my time right now. I also study, and I have papers on this aspect, which are related to supply chain design, but especially closed loop supply chain. So how organizations should model the reverse, what is called reverse supply chain, reverse logistics, while taking into account that there is a forward flow of new materials that need to be produced, manufactured, and delivered to final customer. So how the link of the reverse logistics with the forward logistics work. I have a partnership with a researcher in Tsinghua University, and we've been looking at how the Chinese government gives subsidies specifically for electronic products. So we partner with a manufacturer of large TVs, and we looked at how they deal with the reverse logistics of these huge plasma TVs, how the returns of these TVs was done, how the organization, this company, is getting subsidies for good quality returns, and how they should test these returns. So there's a lot of problems related to testing in order to get the subsidy from the government, how the subsidy should be, what should be the level of the subsidy, what's the total volume of returns, looking at the incentives and so on. And then the last one, as I said, it's just projects that I have with organizations. So I wanted to also, before I get into the paper that I'm going to talk today, I want to share with you my most recent publication, which is an overview of the new area of nonprofit operations. I invite you to take a look at this. This is what is called an OM forum type of paper. It's not a paper that has a modeling part. It's a paper that reviews what has been done in the area of nonprofit operations, which is not per se a lot. We have seen a lot of research in humanitarian relief operations, but not per se when there's no disaster, like when there's an organization that is dealing with regular operations without a disaster happening, and it's a non-for-profit organization. What differs these organizations with the for-profit organizations, and we also in this paper, it's jointly with my advisor, we look at future research questions that are worthy to study and identify the challenges and so on. So I invite you to take a look at this for inspiration for your research, and also look at what has been done as well in this novel area of research. So that's why I'm moving to the next paper, which is today's paper, which also has to do with nonprofit. It has to do with the two blocks that I introduce you today. The block number one related to supply chain design decisions. So when we talk about supply chain design decisions, we're talking about how do we design the network of distribution, right? So where are the warehouse going to be located? So it has to do with location decisions of facilities, and also distribution decisions. So this is how we, when we talk about distribution and location. So the title of the talk, or the title of the paper, location distribution decision. So you have a combination of both location as well as distribution. And then when you're dealing with an NGO that needs to organize this supply chain, okay? So that kind of is like a problem that is very specific for an NGO that is trying to distribute some aid into a region, specific country, specific region in a geographical area. So that's the topic that I'm gonna develop today for you, and hopefully you don't get too bored, and it's something that is useful or gives you some ideas or some inspiration. So how did we get this inspiration actually? Why is this useful, this research, right? So this is useful for many settings, as you will see at the end. I will connect with other applications. But our kind of example that we got started was when we were reviewing what World Food Program is doing. So before I get started, though, I want to let you know that this is a co-authored with Professor Park Chung Park, and he was a PhD student at Purdue, and now he's assistant professor in Korea. So this problem, this inspirational, motivational example, is related to the World Food Program. The World Food Program is the largest international agency that distributes food in the world, right? And they were involved in this post-Civil War crisis in Angola. So Angola had a civil war for many years. And after the war, there was a period that was an emergency period in which the World Food Program participated into delivering food. But after this emergency period, they continued their operations for a while. And this operation was called Protracted Relief and Recovery Operation. And this is important because I wanna emphasize that this is not a relief. It's a relief operation, but it's not a disaster aftermath type of operation. It's not an emergency operation in which there has been a earthquake or something very specific, and we are designing the aftermath. Like aftermath means like weeks after, from weeks to months after. This is later. This is a later type of more long-term type of operation. So there is poverty. There's the mix of the conflict, the Civil War conflict, and also the mix of being in a region that has a large drought. There's not much water in the rural areas, so people who live in the rural areas cannot survive with the means they have, because they have to rely on external food. Basically, they cannot really survive with the food that they can obtain from the fields. So this is, take it as a development type of operation. It's a development type of operation. It's a long-term operation. It's nothing emergent, and it's important because the way we define the objective functions. So depending on the situation and the setting, maybe some other options for objective functions might be more reasonable. So yeah, there's a discussion on that, and I will suggest in this paper, we suggest two performance metrics or objective functions that we think are some of the best ones that could be used for this type of settings. So the idea that for this example was that the World Food Program had studied the several regions in Angola, and to identify which regions were the most vulnerable. So actually, if you go to the reports from WFP, you could find a list of different reports that they call vulnerability analysis and mapping reports, in which they study, they kind of give profiles on different regions within Angola, and they categorize, or they come up with this type of graphs that you have in the slide, in which you can actually assess, for instance, the orange bar is telling you what's the percentage. For instance, the first region, Namibia, the first region has a large percentage. It's 27.4% of the population in that region that is very vulnerable. Okay, and then at 25.8, that is low vulnerable. Of course, the criteria are designed. They look at the household, they look at how much they can consume, where are they located, how much money do they have. So in order to come up with this, it's very exhaustive work that they had done. So what we are suggesting in our paper is, let's use these vulnerability reports that have been done directly. Let's use this directly, because what they observe after this operation was finished, which was finished in 2005, one of the criticisms, or one of the challenges, or we can call it criticisms, was that they wouldn't use these vulnerability reports sufficiently. So I quote here from the report saying, these criteria that the BAM came up with were not systematically used to select the right beneficiaries. Okay, so within each small geographical area, each geographical area was separated and was done the study. There was no difference of treatment between some beneficiaries to other beneficiaries within the region. We are coming up with a way, systematical way, to identify who should be receiving this aid, given the information that was obtained in these vulnerability reports. And this is only an example. The model that I'm going to offer, I'm going to suggest, is a general model. This is only an example of WFP that could actually be using our model. So let me get into a more abstract type of scheme where I'm back into general, right? Here I'm no longer talking about the specific WFP, even though it applies for WFP, but this one is a general scheme, and this is the sort of problem that we are solving here. And I'm sure if you've taken supply chain management courses, you're familiar, especially supply chain design courses, you're familiar with this sort of settings. What we are trying to solve here in an abstract way is a location distribution problem. So the location decisions are going to be these, what we are calling candidate facilities. These candidate facilities are going to be warehouses of food for WFP, but it could be other type of this aid in other different settings. So we have a list of maximum n candidate facilities. And for each facility, we have a fixed cost of location. Okay. And we also have a certain capacity that is associated with the volume of each facility. We also have the demand regions. We can call them regions, we can call them cities. Demand locations, that each specific demand location has a specific total demand, okay, which usually is the population. And one of the novel things of our proposal is that we are going to build a utility function that would be specific for each region, that will be actually giving the utility of receiving certain amount of aid for each region. At each different level of aid you will obtain, we will know what is the benefit that each region can obtain. Depending on the region, depending on the level of aid, there will be a specific utility. So this building of this utility function is one of the novel things of what we are suggesting. And this is specific per each region. And another novelty of this problem is that there is a shortage situation. So there is a shortage situation in the sense that there is a maximum total supply of food that WFP has, or any other organization that's trying to deliver this aid has, in which the sum, so the actual sum of all the population for all the regions is larger than the total supply, right? So the idea is here, well, I cannot really fulfill all the demand, right? So I'm forced to select. I need to select a subgroup of people that will receive this aid, and other people will not receive this aid. So how should we do that? And of course, this raises fairness issues, right? Remember that we are under a setting in which the organization is a not-for-profit organization. So we're not going to be maximizing profit. And we are not dealing with pricing either, because we are just donating. It's important as well. We're donating this food, so we're not obtaining any revenues from this operation. We're obtaining utility from delivering this aid to the population. And one of the things we are claiming is that this utility actually will not be the same depending on who is receiving this aid. We will obtain a larger utility or a lower utility, because it will depend on whether this person is cataloged as highly vulnerable, or average vulnerable, or not secure, which that maybe doesn't even need the food. Okay, so that's what we are suggesting. So I'm moving forward to give you a little bit more detail on these utility functions. So what we're assuming for this is, of course, the domain of these utility functions is the range from 0 to the maximum population of each region. So J is the region. If we focus on a specific region, every region has a specific utility function. and the domain goes from 0 to the maximum population of this region. And then, of course, the range will be the maximum range, would be the maximum utility. And if we got to give the aid to all people in that region. Okay, that's how we define this notation for maximum possible utility. So the way we're defining these utility functions is through, and of course, increasing. We're doing piecewise linear because we are assuming that we are separating the population in each region into different type of population. As you can recall, some slides before, I was differentiating between very vulnerable, right, low vulnerable, and secure. And so these are kind of the separations. So, and actually WFP did these separations, and it's not the first time they do this for different crises of different regions. So what we are assuming here is that we can categorize different populations within the region into more vulnerable, medium vulnerable, or not vulnerable, okay? So of course, the ones that are more vulnerable will be given a utility or a marginal utility. So this is the slope of this function that is larger, a larger slope. And then as we use criteria for less vulnerability, the marginal utility will be more flat, okay? So that's the way we're doing. And of course, this is also monotonic decreasing. As I said, it's just a description, right? So for population that is less vulnerable, the utility of obtaining or receiving this aid will be less beneficial because they don't need this aid. So for the population that most need the aid, the benefit of receiving the aid will be larger. That's why it has this sort of concave shape, this utility function. So contribution of this study. So we have contributions related to the modeling part, and you'll see how the modeling of this, one of the novel parts is that we are suggesting two objective functions. We're claiming that there should be a combination of maximizing efficiency, and you'll see how we define efficiency, as well as minimizing inequity. So we should try to be fair in our distribution, but we shouldn't focus only on fairness or on inequity. We should also be looking at how efficiently this distribution is being done. And by efficiency, we take into account the maximum utility obtained of delivering all the aid. And also we take into account cost, okay, cost of the operation. It's part of the efficiency. So the other contribution of this work is also methodological, because we are giving two fractional objectives. And this is a complex structure because we have two fractions, right? So if we only had one fraction, we could linearize the fraction and we would end up with a linear problem, but we don't because we do have two fractions. So we provide a way of solving this optimization problem. And we also theoretically look at some complexity bounds of the methodology that we're suggesting. So we go a little bit technical into that aspect. And then the last contribution here is also the fact that we are showing applicability of what we're suggesting in theory, right, through a specific real example. So these are the three contributions. There's literature, different literature can be similar to what we do, not entirely the same, of course, because otherwise we wouldn't be contributing, right? But there is, if you look at the literature related to equity and efficiency, there are different metrics that have been suggested. The ones that I'm presenting here are new. I will tell you how new they are, right? Why are they new, right? But there are, if you're curious about this, on facility location analysis, the area of facility location has several papers. And by the way, the paper that I'm presenting, this paper has been very recently published. So you can look at all the literature, all these references. If you Google the title of today's talk, you can find the paper. I had shown it is a POM Journal, Production of Operations Management, has recently published the paper. And you can look at all the references. All of the references that I'm quickly reviewing here are listed there in detail. So you can go there and check this out. But what I mean to say here is that there's for sure research that discusses equity in facility location. So, but most of the equity measures that have been so far introduced in facility location analysis have been related to analyzing or using distance. So distance between beneficiary and the potential location of the facility. Distance or time of travel. And seeing, well, comparing how far away one beneficiary is from a candidate facility and how far away another beneficiary is from the same candidate facility, and trying to find the optimal facility location looking at distance or travel time. What we are suggesting here is, well, we are saying, okay, shipping cost or distance is important, but let's look at also the utility, the benefit of having receiving this aid for each specific individual beneficiary. And let's take into account this utility into the inequity function. Okay, so the specific equity, because there's a lot of equity measures that are suggested. If you go to Marsh and Schilling, 1994, it's kind of a seminal paper on equity. You will find a lot of different equity metrics. One specifically that also we are basing our equity measure on is the Gini coefficient. So the Gini coefficient is an index. So initially it was defined as Gini. It's defined, if you look at the literature, Gini index is used in economics, was initially used in economics, but there is a paper, an initial paper on, it's a management science paper, this Mandel 1991, that for the first time uses the Gini index, and they call it Gini coefficient. He calls it Gini coefficient for resource allocation problems. And I will talk a little later about how the form of this objective looks like, and how are we suggesting we build on top of this one. So this is this seminal paper from Mandel, and then there has been other work related to Gini coefficient. I believe this one should be, it's an OR paper, the last one, an OR paper. I think they published 2019 or 2020. I'm not sure. It's kind of, when I first reviewed that was a working paper, but now it's published in the Operation Research Journal. They also use the Gini coefficient, okay, in this one. This one is this third paper here is more related to vehicle routing. So not only facility location, also in vehicle routing problems, this Gini coefficient and other equity measures have been used. Applications have been a few in the area of food delivery. Applications of, what I mean is applications of not Gini coefficient here, it's more general. Applications of efficiency and equity in general, equity or inequity metrics. Not these ones specifically, they don't use Gini, but they use other inequity measures and efficiency and effectiveness measures. Food delivery is one area. Disaster relief is another area. Healthcare is also a popular area for this type of problems. Think about this. We are talking about delivering aid. So these are applications that are kind of a good match for the specific aid distribution settings. So in going more technical on the solution methodology side, what we are dealing with here in this paper is this structure, this optimization structure. So we have integer linear fractional problem. Okay, so what's the structure of this type of problems? The structure is that in the objective you have a fraction that is linear, in the sense that in the numerator you have a linear function, in the denominator you have a linear function, and then the constraints are linear too. Okay, variables are integer, and then of course you need to make sure that the denominator of this problem is non-zero, right? Because you don't want to run into problems with having like infinity solutions and things like that. You need to make sure that this is positive the denominator is positive, okay, to keep feasibility. So looking at, this is just a review within the literature review part, looking at methodologies to solve, existing methodologies to solve integer linear fractional programs. And the one that we're suggesting for this paper is related to parametric algorithms. And I will give you a little bit more detail later. And also the contribution, this more technical contribution on looking at complexity bounds, because we're focusing on parametric algorithms. So we are actually improving or giving suggestions for complexity bounds for parametric approaches, specifically we look at the Newton method and sub-approximation method. So going back into the methodological contribution, sorry. So I wanted to highlight this contribution related to complexity bounds. And moving forward, these are the kind of the research questions. The main problem is how to allocate a supply among different demand locations when the supply is below demand levels. Okay? And then the central questions are how to address fairness while also looking at efficiency, or also keeping good efficiency or high maximum efficiency. And the other one is how to integrate what we are calling location and diminishing returns effects that I will discuss later. In a way, the second question is related to how do we take into account that not all beneficiaries are the same, that there's more vulnerable beneficiaries than others, and also that there's regions that are overall better off than other regions. In a way, what we are saying is we shouldn't treat all the individuals the same, okay? We should treat them depending on their level of vulnerability. Okay, so that's this is the problem, the optimization problem. And we do have, well, the way we structure this is we are maximizing efficiency, we are minimizing inequity, and this small u refers to what we are calling utility-based Gini coefficient that I will introduce you in a few slides. And then these are the constraints. I can quickly go through these constraints right now because we have everything together here. The first constraint is just making sure, and that's something that we are assuming here in this problem. We're assuming that we know in advance how much supply we have, and we are going to assume that we're going to distribute all the supply. This is what this constraint is making sure of. The second set of constraints is making sure that every region will receive a volume of aid that is not surpassing the demand of the specific region. Okay, this is just regular demand constraint. This fifth set of constraints relates to the capacity constraint, which is also quite standard. So we cannot really commit to deliver a level of volume of food or whatever aid that is beyond the capacity of the warehouse that we're going to use. Okay, so basically we're making sure the capacity constraint for a facility, for a warehouse, is not exceeded. We are not committing to delivering more than the capacity of the warehouse. And then we have the usual constraint here. It's integer constraint for the distribution aspect. So we're distributing, we are trying to define how much should be distributed from warehouse I to demand location J, but we also are deciding at the same time whether we should build a warehouse or use a warehouse in candidate location I. Okay, and that's a binary variable. So these are, if you're familiar with location distribution problems, a lot of these should sound familiar to you. I'm going to introduce, as I said, we have two objectives. The first one is a maximization of efficiency. And this is the idea behind this is the following. We can see any process as a black box, right? As a black box of the process in which there's input and there's output. So a process or an operation, if you will, we can call it operation in our setting because we are not in a manufacturing plant. Usually these diagrams are used for manufacturing plant in which there's a manufacturing process, right? And raw material and then outputs. Here, there's there's an operation and we have an input, which is food, and this input needs to be delivered to the beneficiary, right? So the idea of efficiency is simple. It's general. The general idea of efficiency is when I want to say something is efficient, I'm trying to maximize output while I minimize input, right? So it's a trade-off. The idea of efficiency is let's take care of this trade-off in which we care about maximizing output, as much delivery as possible or as much benefit as possible, but also taking into account that I don't want to spend a lot of money or I don't want to spend a lot of resources, right? Or labor, whatever the specific setting you are in. So in thinking of this general idea, which is the first bullet, we suggest the following definition of efficiency, which is a ratio between the numerator. As I said, it should be an output measure. This output measure for us is going to be the utility, maximum utility delivered. Okay, so the delivery variables are here. These CJTs are the coefficients of the utility function. So in a way where I could have give you a more general formula here, but what I'm doing here is the sum. I think all the utility functions. Remember that it was a piecewise linear function. That's why it's a linear sort of summatoria here. And we have just coefficients, but this is just the overall utility that I'm providing by delivering this aid. Okay, and the denominator are the costs of this operation. And in this setting, we are assuming that we have the location cost, the usual cost of the supply chain design problems, right? The location cost, the cost of locating a specific warehouse in a specific candidate location, and the shipping costs that are related with the distance between the warehouse, each candidate warehouse to each specific region. Okay, so yes, we are suggesting this, and of course it's complicated because we have variables, and these variables are in the denominator, which makes this objective a fractional objective. So just briefly, I want to go fast because otherwise I won't have time to go through the whole thing. What this example is trying to illustrate is the benefit or the difference between having only maximization of utility. And a lot of times the maximization of utility or the maximization of output is, and in a lot of papers, is used without taking a look at cost. And we are claiming that costs are also important. And it's especially for nonprofit organizations, there's now, and it has been going on for years now, but there's starting to be a movement in which, we should be taking care of what is called value for money. So it's not only enough to deliver as an NGO, to deliver to the people in need. There should be accountability. How do you do that delivery? Is this delivery done using the budget as much, wisely as possible? So what we are suggesting with this measure is saying you should definitely maximize utility, but also take care about the cost. Okay, don't throw the money that you are given for this operation away. Just use it wisely too. So some papers before our paper, when we were doing the literature review, we observed that a lot of papers use what they don't call it equity measure. They call it effectiveness, like looking at effectiveness. When you look at efficacy, is when you are looking at to maximize output. So if you're only maximizing output in this setting, and let me explain this setting. Well, you have let's assume that we have 4 units of supply. We have a warehouse, a unique warehouse. So there is no, let's remove the location problem here. We have 1 warehouse. We have 2 demand regions. Each demand region has 4 people, or we can call it 4,000 people, 4 people in each. Okay. The cost of delivery for from the warehouse to the first location is 1. However, it's cheaper to distribute to the second location, 0.8 if you only distribute either 0, 1, or 2. But it's cheaper when you go and distribute at a larger volume. So for the 3rd and 4th supply units, it kind of it's a bargain. It's cheaper, so it's 0.6. So what we're saying is, if you were only minimizing cost in this operation, if you were only looking at minimizing cost, the solution would be to deliver everything to demand 4, because you're only trying to minimize cost, right? If you're doing the opposite and only trying to look at the utilities, and the utilities are different, we're assuming they are different here. For demand region 1, we're assuming that everyone has the same utility, everyone is in the same level of risk. And this level of risk is actually vulnerable, but not very vulnerable. See demand 2. Demand 2 has the first individual, which is highly vulnerable, actually more vulnerable than the individuals in demand 1. And then the second and third and fourth, they have less need per se. So one key thing to observe here for this setting is that the second beneficiary here has a slope that is actually flatter than the slope of all these individuals here that are exactly the same. So looking at this utility behavior, and if we were only maximizing utility, the solution would be, let's give 1 unit to the first individual in demand location 2 and the rest to demand location 1. So that would be exclusively, we look at maximization of utility. But if we are looking at maximizing efficiency, what we are recommended to do is to do 1 here. Looking at these numbers, we would distribute 1 unit for demand 1 and then 3 units for demand of type 2 or region 2. So it's, it's what we are trying to show here is substantially different, the solution, depending on what objective you have. Now, focusing on the second objective function. Second objective function has to do with, as I said, maximization of inequity. So we look at fairness problems. And as I said, we are looking at the Gini coefficient. The original definition of the Gini coefficient is through the Lorenz curve. This is in economics, in which you have a region, usually it's per country. So you have the x-axis. The x-axis is the proportion of, you kind of rank the population from lowest income to largest income. And you say, for instance, 10% of most poor in the population, how percentage of the overall income do they have? So the 10% poorest might have like 0.02 of the income. That's 1 point here. So that's the Lorenz curve. Of course, if the Lorenz curve was exactly like falling on the diagonal here, that would mean that there's no inequity. So every specific citizen has the same income, receives the same income. That's kind of utopic. It doesn't exist in any country. But the more, the larger this blue area is, the more convex this Lorenz curve is, the more inequity that exists in a country. Okay, that's kind of the idea. So if we extrapolate this idea, and that's what Mandel did in his work, he put he algebraically defined the Gini coefficient with the idea of resource allocation problem in mind, in which xj is the resources received in region J, given that the overall demand of that region was Bj. Okay, so he's sort of, this is kind of the idea of envy function. So comparing what each region receives with each other, right? So xj and xk are the decision variables. So how much should each region receive, given that each region has a maximum population? Okay, so this is this is a proportion. It's a number between 0 and 1, and if you are trying to minimize this overall function, what you're trying to do is trying to minimize this difference. So minimizing the proportions that we are giving to each region. So what's happening here for this Gini coefficient? The idea for if we apply this Gini coefficient to our problem, what we would have, that the total distribution would be S, because we are making sure that we are delivering all supply, right? So the benefit of using this Mandel Gini coefficient for our problem would be that we have, this would be non-fractional, because we have a denominator that is a constant, because the overall sum of all the delivery, or all the aid, is the supply. But this is because this Gini coefficient per Mandel, in the way Mandel defined it, he was assuming that everyone, every single individual in every region was exactly the same, were representing the same need. So in a way, thinking about this, every individual, or he was actually using the identity function. If you're trying to define a utility function that represents the benefit of receiving the aid, what he was saying there's no difference between people in terms of the benefit of receiving aid. Okay, that's what he was using. What we are suggesting under the situation that we are now, you've already seen this graph, is that we don't have an identity function. An identity function would be a straight line, right? A straight diagonal. We are saying there's more benefit for the population that has more need and less benefit for the population that has less need. So it shouldn't be defined as identity matrix, as identity function. It should be defined. We're suggesting this other definition of utility in which you have piecewise linear function that has a concave shape. And if you do that, then this definition, and that's why we call this utility-based Gini coefficient, this definition of the Gini coefficient changes to this formula. And technically this is more complicated now, mainly because we are no longer having a constant in our fraction. The denominator is not a function anymore, because the overall sum of all the utilities. So if we look at now, instead of looking at comparing the proportion of population covered by the aid, we are looking at the proportion of utility generated or utility obtained by aid divided by the maximum utility possible. And we are doing that, then here we are summing all the utilities, the sum of all the utilities, because our utility functions are not the identity. This is no longer a fraction, the denominator is no longer a fraction, and everything gets a little bit more complicated. I'm going to skip this example because I don't have enough time. I want to highlight the most important part of the paper. I don't want to bore you either. There have been in the literature some properties of inequity measures. That one is the principle of transfers, in which it's said that equity measures should have the principle of transfers. Equity measures should follow the scaling invariance aspect. What we are saying, we are reviewing these principles, or we can call them principles, we can call them properties, applied to our utility-based Gini coefficients, and we are observing that under our suggested measure, for a general utility function, these two properties are not gonna be necessarily satisfied. So they will only be satisfied. One, the principle of transfers will only be satisfied if all the utility functions, we use the same exact utility function for each region. But we are saying there's no need to do that. We can customize. We should try to customize the utility functions per region, because every region is different, right? Every region might have, in our setting, every region has a different breakdown. So the breaking points between the different slopes, the breaking points that differentiate one slope with the next slope, are defined as the percentage of population who are highly vulnerable versus less vulnerable. These breaking points are in different places depending on the region. So naturally, in our setting, we don't have we're not using the same utility function for each region, and we don't have neither the same coefficient in general, right? So what we are claiming is that we are taking into account aspects that are what we call location effects. So we are saying we take into account the location effect, which is every utility distribution is different in every region. And we're also taking into account what we call concavity effect, which says within each region, not everyone is the same. Okay, so there's people that need it more than less. So that's why we have a concavity function, and we call this concavity effect. Anyway, so when we max the overall, two expressions of the objective are these two. Note here that we had a absolute value here. We had to linearize. This is technical stuff that we did in the paper. We use some auxiliary extra decision variables to linearize the absolute value here, but we're still coming up with the fact that we have two objective functions that are fractional. Anyways, I'm presenting here the decision variables. The decision variables, I've already talked to you, the distribution variables and the facility location variables type of setting. These are the breaking points that I was suggesting, or I was mentioning before, that are important, because you need to know when the slope changes, right? So because in a way what we have is the distribution. Our distribution variables are actually defined per each t. This t is the range of each interval. So we not only we decide how much should be received in each region, we also say if t is 1, we're talking about the first interval. If t is 2, we're talking about the second interval. If t is 3, the third interval. One thing to note is that there's no, by definition of the optimization problem, we will never receive, or the optimal decision will never, will never deliver 8 into, let's say, T3 if T1 and T2 have not been completely fulfilled. This is because of the concavity effect. So also naturally, always we will be always fulfilling from this side to this side, right? Anyways, so the constraints I've already talked about, so we can skip those. And these are more technical linearization constraints. I wanted to quickly lead you through the two-phase algorithm that we defined for solving this problem. So what we basically did was we selected the maximization of efficiency, and then we linearize. We are using the epsilon constraint method to put the second objective, that is this minimization of inequity, as a constraint. Okay, if we do that, we can in a way solve the problem of the second fractional objective. However, we still have a fraction, one of the fractions in the objective. And usually, we solve this epsilon constraint approach. This is phase 1. And then the phase 2 is, once we solve this problem in phase 1, and of course, this problem will depend on the epsilon value that we have. For each epsilon value, we have a different solution for phase 1. Then, given the solution of phase 1, we'll have integer linear program, which will find the solution of the minimization of inequity part. Okay, so we'll need to phase 1 solution to solve the phase 2 solution, and then phase 2 solution is an integer linear program that is easy to solve. The problem is how to solve the ILFP problem. And the way we solve ILFP problem is through parameterization, parameterizing. And how we parameterize is we use the parameter lambda. This is very generic in the literature. Usually this alpha lambda is used. So we are maximizing this expression. Okay, we find this equivalent expression of the ILFP. And we are trying to solve, let me give you the right notation, we denote H lambda, this optimal objective, and we are trying to find the root of this function here. This H lambda is the whole objective here. Okay, and then there's different ways of solving this problem. Historically, this can be solved using the Newton's method. Right. Yeah. So this would be the H lambda function, the blue function here, and the idea is how to find, using iterations, how to find the root of this lambda, which will give us the solution of the initial problem, the ILFP problem. Okay. So the sub-approximation algorithm is also using a similar idea, but instead of starting off from this side of the problem, we're actually combining both bounds. We are looking at upper bound and lower bound, both bounds, lambda min and lambda max, to try to get as fast as possible to the root of this function. Okay, so this is a little technical, but we went beyond that. We went and looked at how the complexity, what kind of revised the theory on the complexity bounds for ILFPs. There is some results from 1993 related to binary variables, and we kind of could improve these results. So from going to n squared log square n, we improved this. We gave more precise results here, and also for the subapproximation algorithm, we could give complexity results that would depend on some of the parameters of the problem. We did computational efficiency studies to make sure that our two objective or two-stage approximation algorithm was good enough. We observed that the subapproximation between choosing Newton or subapproximation method for the parametric part was better off, especially when the denominator, when the location, facility location function or denominator part of the efficiency metrics was particularly steep. So we observed that subapproximation was behaving a little better. And most importantly, because I don't know if you're familiar with production and operations research and production and operations management journal, which is the journal we published in this paper, is a journal that is more OM-like. It's more operations management. So the editor, the reviewers were more interested in obtaining managerial insights than looking at, even though they actually gave us very good feedback on the algorithm side as well, but they also wanted to subtract interesting managerial insights. So we could run several experiments on that, looking at how the problem behaved when we, for instance, increase supply. When we increase supply, we could observe that more facilities were open. We could also look into efficiency levels, and it's an interesting result here. If you increase the supply, efficiency is not clear if it will go up or down, because remember that efficiency not only takes into account maximum output, it also was looking at minimization of cost. And if you are increasing supply, you're going to increase more money, you're going to pay more money because you have more supply to deliver. So that's another, that's one aspect that it's not necessarily expected. Well, it's expected if you take the approach of defining efficiency the way we did, which is also taking into account the cost aspect. And of course, inequity was getting better, because the more supply you have, you are helping more people. So inequity has also opportunity to improve, in the sense to reduce. Okay. Other managerial insights. So because we are using the epsilon constraint method, we were playing with the idea of allowing more or less inequity, because the epsilon, if you remember, what I was using is the epsilon was attached to the inequity objective, in which I put the inequity objective as a capacity, as a constraint, and this epsilon kind of represents the maximum allowable inequity that I'm allowing in the problem. So it's interesting to see if I'm allowing more inequity, how the problem changes. So when the maximum inequity, I'm allowing less inequity to happen, okay, the number of facilities tends to increase, because we gotta naturally distribute to more regions. We gotta naturally distribute to more regions because we gotta naturally distribute to the most vulnerable population of each different region. Okay, we gotta cover the most in need, and the most in need at certain point of supply, we're jumping to the next type of beneficiary which has less need. So what is forced this forced us, when we decreased the allowable inequity, was that we had to suddenly supply to a new region because there were more vulnerable people in that new region. Anyways, I want to try to finish. There's more interesting managerial insights. The first three are important, and then the last part of this, as it's an operations management type of journal, they also put a lot of emphasis on showing how are you gonna, for instance, create this utility function for real, right? So that the most interesting part here on the case studies, how are we building the utility function for each region? And this is the way the utility functions look like. So we were using exactly the same slope, depending on the type of, we were using actually arbitrary numbers, 4, 3, 2, 1. So 4 would be attached to the set of individuals that were most in need, and so on. So the most insecure, and then the highly vulnerable, moderate, and low. So we are assuming higher coefficient for the most in need, but we were assuming the same coefficient for all the regions. That means that because we were delivering the same basket of food to each region, we were assuming that the benefit of receiving one basket of food for a food insecure person would be the same regardless of the region, as long as this person was cataloged as food insecure, for instance, right? So, but as I said, it's also important to see what's the breakdown of the proportion of how many people in each specific profile each region had. And that's why you can see that the utility functions for each region are differing. Also, another aspect that was differentiating was the total volume of each region's population too. So we ran the problem using these utility functions per region, using all the data related to cost, related to distances. We were using Google Maps for distribution of distances, the cost of the facilities. We were using the real numbers. And then, of course, the interesting part is, well, what you can do in this type of a study? Well, you can do what is called a trade-off curve. You can show a trade-off curve in which each point will be the solution of how much should be of this trade-off between inequity and efficiency, depending on this epsilon. The epsilon is actually the volume. The epsilon is the maximum allowable inequity that we are offering. So each point was the result of setting a specific epsilon, and so you can see that at certain point there's trade-offs, and for instance, between these two options, one might prefer this point on the left because the difference in terms of losing inequity is substantially large, but the difference in terms of improving efficiency is almost negligible, right? So these sort of decisions are interesting to see. Anyways, I think I'm going to finish up. There's the extension for the research, plenty of extensions. There's continuous discussion on objective functions. There is also discussion on how, because we were using arbitrary numbers for the coefficients of the utility functions. We were using 4, 3, 2, and 1 of the case study. How can you come up with a systematic way of assigning values to these coefficient values of utility functions? That's something that I think we would like to improve, right? And it's improvable. How do you solve this problem where you giving aid for multiple types, not only food or different type of food, right? So when you have a multi-commodity type of case, this is also something interesting to develop. We could also look into the improvements on the solution method side too, which is a little bit more technical. With that, I want to finish.